here's something that should stop you cold. The universe keeps a perfect record of everything that has ever happened in it. Every star that ever exploded, every photon that ever crossed empty space, every quantum whisper carried by a single particle, all of it, logged, permanently. That's not poetry, that's the law. Except black holes seem to be the one place where the universe quietly broke its own rule, shredding the pages, one evaporating photon at a time. In 1997, Stephen Hawking put that idea on the table as a bet. The stake was a baseball encyclopedia. The question, whether a black hole destroys information forever, seemed almost too clean for a wager. For 30 years, the smartest people in theoretical physics couldn't prove him wrong. And then, in 2019, they did. Except the answer they found didn't just fix the leak. It suggested the pipe, the water, and the entire plumbing system aren't quite what we thought they were. It told us something deeply unsettling about what black holes actually are. If you're new here, hit like and subscribe. Settle in, get comfortable, because tonight we trace a single thread that runs from a calculation Stephen Hawking wrote in 1974, through a bet placed in a Caltech office in 1997, all the way to two groups of physicists who, 5 days apart in 2019, independently pulled on the same loose end of reality and found the same answer. Now, let's slowly ease into this. Part 1. The Encyclopedia and the Ashes. There is a moment in the history of physics that the cameras got completely wrong. July 21st, 2004, a conference hall in Dublin. The most famous physicist alive rolls to the podium in his wheelchair, and the room goes quiet in the way rooms only go quiet when something genuinely historic is about to happen. Stephen Hawking is about to concede a bet he has defended for 30 years. He's about to hand over a baseball encyclopedia as payment. He's about to make a joke about ashes. And almost every news organisation on the planet is going to report that a great scientific question has finally been settled. The physicists in the room know something different. They have spent their careers on this exact problem. They have read every paper Hawking published on it. They are watching the most celebrated theoretical physicist of the late 20th century change his public position, and the quiet consensus moving through the audience is not relief. It is something more like unease, because the people who actually understand the question know that the question has not moved an inch. Let me tell you what was actually at stake. In 1997, at the California Institute of Technology, Hawking and his colleague Kip Thorne bet their friend John Preskill an encyclopedia of the winner's choosing. The wager was simple to state and impossible to answer. When a black hole evaporates, what happens to the information of everything that fell in? Hawking and Thorne said the information is destroyed, gone, not hidden, not scrambled, erased from the universe entirely. Preskill said that cannot be. If it is, then quantum mechanics, the most precisely tested theory in the history of science, is broken at its foundation. That is the bet. And I want you to sit with the scale of it for a moment, because it is easy to hear the information paradox, and think of it as a technical debate between physicists who spend too much time at whiteboards. It is not that. It is a question about whether the universe keeps a ledger of everything that has ever happened in it. It is a question about whether the past is real in any deep sense. If Hawking was right, then every star ever swallowed by a black hole, every photon that ever crossed an event horizon, every quantum state that ever fell past the point of no return, all of it is simply gone. The universe in that picture occasionally tears a page out of its own record book and burns it. Not misfiles it, burns it. Quantum mechanics says that is impossible. The rule is called unitarity, and it is not a suggestion. It says that the evolution of any closed quantum system is reversible in principle. Information about the initial state of a system is always preserved, scrambled, hidden, encoded in correlations so complex that no practical technology could ever read them, but preserved. Drop an encyclopedia into a furnace, and in principle, a sufficiently powerful demon could reconstruct every word from the pattern of smoke and ash and heat and photons radiating off the fire. The information hasn't gone anywhere. It has just become extraordinarily inconvenient to access. Drop that same encyclopedia into a black hole, let the black hole evaporate, and according to Hawking's 1976 paper, the words are gone. Not inconvenient to access. Gone. That is not a subtle distinction. That is a direct contradiction between the two pillars of modern physics. Either the most successful theory of the very small is wrong at its foundation, or the most beautiful calculation Stephen Hawking ever performed is wrong. There is no third option. Someone is wrong. And for 30 years, the smartest people in theoretical physics could not figure out who. The reason the Dublin concession feels hollow in retrospect, and this is the part that the news coverage missed entirely, is that Hawking's proof at the conference was not accepted by the audience. He presented an argument involving sums over different black hole topologies, which is a technical way of saying he was counting up contributions from different possible geometries of space-time. The argument was suggestive, it was not a proof. John Preskill accepted the encyclopedia that afternoon, and later admitted publicly that he didn't think Hawking had solved it. Kip Thorne refused to concede at all. He has never paid his half of the bet. As of 2026, the bet is technically still half open, and Thorne remains the last holdout from the original wager, stubbornly and not entirely unreasonably sceptical that the problem has been fully cracked. But something did happen in 2004, not a solution, but a shift. Hawking's concession changed the sociology of the problem. After Dublin, it became more acceptable to say openly that information probably escapes. The minority position started becoming the majority position. And then, 15 years later, something extraordinary happened. Two independent groups of physicists working in different countries, using slightly different mathematical tools, posted papers to the preprint server arXiv within 5 days of each other. And they had both derived the same thing. The curve that the answer had to follow, derived not from quantum information theory imposed from the outside, but from the equations of gravity itself. That result, from the spring of 2019, is what this video is really about. Because the answer they found does not just resolve a 50-year-old bet about information. It suggests that the inside of a black hole and the outside of a black hole are not actually separate places. It suggests that the geometry of the space you're sitting in right now, the distances between things, the number of dimensions you can move through, the apparent solidity of here as opposed to there, may be a projection of something simpler, hiding behind everything you can see. And before we get there, I want to give you one more data point, because it makes everything else land harder. On January 14th, 2025, the LIGO gravitational wave detectors recorded the loudest black hole merger ever observed. The signal-to-noise ratio was 80, roughly 3 to 4 times clearer than the previous record. For the first time, scientists could hear a black hole ring down after collision, with enough clarity to identify 2 distinct harmonic overtones, matching the predictions of general relativity to within a few percent. Every test of Einstein's theory that could be run on that signal was run. Every single one passed. The Kerr metric, the area theorem, the ring-down frequencies. Black holes are real, and they behave exactly as general relativity predicts. Here is the thing that should stop you cold. We have never been more empirically certain that black holes exist, and we have never been more theoretically confused about what is happening inside them. The outer shell of the mystery has been confirmed to unprecedented precision. The interior remains the strangest problem in physics, and the two facts are not in tension. They are in a way that will take the rest of this video to explain, pointing at the same terrifying conclusion. So let's go back. Let's go back to 1974, to the moment when Hawking performed the calculation that started all of this, and let's actually understand what he found and why it kept him up at night for 3 decades. Part 2. What Hawking actually calculated. Stephen Hawking in 1974 was doing something nobody had managed to do before. He was asking what happens to quantum fields, the quantum mechanical description of matter and radiation, when they live near the curved spacetime around a black hole's event horizon. This sounds technical, and it is, but the intuition is not so hard. General relativity describes gravity as curvature. Spacetime bends near mass, and black holes bend it so severely that beyond a certain radius, the event horizon, nothing, not even light, can escape. Quantum field theory describes particles and radiation as excitations of underlying fields that fill all of space. Normally, these two theories live in separate rooms. Hawking wanted to know what happens when you put them in the same room, near a horizon. The answer surprised him. Black holes are not perfectly black. They glow. The intense gravitational field near the event horizon causes pairs of particles to be spontaneously created out of the vacuum. One particle falls in, one escapes, and the escaping particles carry energy away from the black hole. The black hole radiates. It has a temperature. The more massive the black hole, the colder it is. A solar mass black hole has a temperature of about 60 nanokelvin, that is 60 billionths of a degree above absolute zero, which is so cold it makes interstellar space look like a sauna. The supermassive black hole at the centre of our galaxy, Sagittarius A star, has a temperature of roughly 1.5 times 10 to the minus 14th Kelvin, which is a number so close to absolute zero that writing it out barely helps. So let me try it this way. The cosmic microwave background radiation that fills all of space is about 2.7 Kelvin. Sagittarius A star is colder than the universe around it by a factor of about 200 billion. It is absorbing more than it emits. It is right now growing. The radiation was a beautiful result. It connected three of the great pillars of 20th century physics. General relativity gave the black hole, quantum field theory gave the radiation, and thermodynamics made sense of the temperature. Jacob Bekenstein had already argued a year or two earlier that the entropy of a black hole, the measure of its disorder, the thing that always increases, was proportional to the area of its event horizon, not its volume. This was strange. Entropy usually scales with volume. A room with twice the volume can hold twice as much disorder, but Bekenstein said black hole entropy goes as area, and Hawking's radiation calculation gave that entropy a temperature and put the whole thermodynamic picture on firm footing. But the calculation also produced a paradox, and Hawking understood it immediately. The radiation was thermal, not just nearly thermal, perfectly, mathematically thermal. It was characterized entirely by its temperature, and its temperature was determined entirely by the mass of the black hole. It carried no information about what had fallen in. The radiation from a black hole that swallowed a single hydrogen atom would be, in every measurable way, identical to the radiation from a black hole that swallowed an entire library. Same temperature, same spectrum, same randomness. The specific content was invisible. And here is the thing I want you to really feel, because this is the core of the problem and everything that follows depends on it. Go back to the furnace analogy. You burn the encyclopedia. The photons and ash and smoke that come out are in principle correlated with the original text. Not because they look like letters, they don't, but because quantum mechanics says every physical process preserves information. The correlations are there. They are encoded in the precise quantum states of billions of particles moving in specific directions at specific energies. And yes, reconstructing the encyclopedia from the smoke is so wildly impractical that it might as well be magic. But the information is there in principle. Quantum mechanics guarantees it. Hawking's radiation doesn't work that way. The radiation is generated by the geometry of the horizon, not by the specific matter that crossed it. The horizon doesn't care about the encyclopedia, it cares about the mass, and mass is a coarse average of a lot of things. You can have the same mass in 1,000 different configurations, and they all produce the same horizon geometry, and they all produce the same radiation. The information about which configuration you started with is not in the radiation. It is not anywhere accessible outside the black hole, and when the black hole finishes evaporating, when it has radiated away all of its mass and disappeared entirely, there is nowhere left for the information to be. It is gone. Hawking published this conclusion in 1976. He knew what it meant. He was not careless about it. He was saying, explicitly, that black holes cause pure quantum states to evolve into mixed states. In the language of quantum mechanics, a pure state is a system where you have maximum information. You know exactly what quantum state the system is in. A mixed state is a statistical ensemble, a probability distribution over possible states. Pure to mixed is irreversible. It is information destruction. It is a one-way door that quantum mechanics says should not exist. Think about what that actually means for the universe. The universe began in some particular quantum state. Everything that has happened since, every particle interaction, every stellar explosion, every civilization that ever rose and fell, every photon ever emitted, has been, according to quantum mechanics, a unitary evolution of that initial state. In principle, you could run it backwards. The future contains the past, encrypted. The past contains the future in the same way. The record is perfect and total. Hawking's black holes punch a hole in that record. Information falls in. The hole evaporates. The record is incomplete. The universe, in Hawking's picture, occasionally just forgets. For 30 years, most theoretical physicists were quietly convinced that Hawking had made an error somewhere. They could not find the error. The calculation was airtight. The error was not in the math. It had to be in an assumption somewhere, some approximation, some place where Hawking had treated the space-time as classical when it should have been quantum, or treated the radiation as independent when it should have been correlated. The error was there. Nobody could locate it. And then, in 1993, a former student of Hawking's did something that reframed the entire problem. He couldn't find the error either, but he figured out exactly what the answer would have to look like if there was one. Part 3. The curve that waited 26 years. Don Page is not a household name, which is a real shame because what he did in 1993 is one of the most elegant moves in the history of physics. Page had been Hawking's student. He knew the information paradox from the inside. He couldn't crack it. But he realized something. Even without knowing the mechanism, he could specify precisely what the solution had to look like. The tool he used is called entanglement entropy. When a black hole evaporates and emits radiation, the radiation becomes quantum mechanically entangled with the black hole's interior. Entanglement entropy is a measure of how entangled two systems are. It goes up as entanglement grows, and it goes down as the entanglement is resolved. Page's argument was deceptively simple. If information is preserved, if quantum mechanics is right and the universe keeps its ledger, then the entropy of the Hawking radiation must follow a specific curve. It starts near zero when the black hole is young and has barely radiated anything. It rises as the black hole evaporates and more entanglement accumulates between the radiation and the interior. It peaks at a particular moment, the Page time, and then it must turn around and fall. By the time the black hole is completely gone, the radiation has to contain all the information that was inside, and its entropy must return to whatever it was at the start. Hawking's calculation predicted something completely different. In Hawking's picture, the entropy of the radiation just rises. It rises monotonically, all the way to the end. It ends at the maximum possible value, as if the radiation had completely forgotten everything and become as random as it possibly could be. There is no turnaround. There is no Page time. The curve just climbs until the black hole is gone, and then it stops. These two curves agree at the beginning, when the black hole is young. They start to diverge as the evaporation progresses, and they are completely different by the end. One of them is right. One of them describes a universe that keeps its ledger. The other describes a universe with a leak. And for 26 years after Page drew his curve in 1993, nobody could derive either one from the actual physics of a real black hole. I want to give you a sense of how long 26 years is in physics time. The field of quantum computing went from a theoretical proposal to running practical algorithms in about that time. The Hubble Space Telescope was launched, operated, and transformed our picture of the universe during that window. The field of gravitational wave astronomy went from a dream to detecting hundreds of black hole mergers, and through all of that, the Page curve sat there on a graph, specified precisely, and nobody could derive it from first principles. Physicists called it the most important unsolved problem in theoretical physics. They weren't being dramatic. There is something philosophically specific about having a problem where you know the shape of the answer, but not how to get there. It is like looking at the shadow of an object you cannot see. You know the object has a certain shape, roughly rectangular, maybe, with a handle on one side, but you cannot see the object itself. The shadow is exactly specified. The object is somewhere in the dark. Page's curve was the shadow. The actual physics of information escape was the object, and the search for it, over 26 years, is the story of how physicists ended up overturning not just their understanding of black holes, but their understanding of what space is made of. But let me also tell you something about the page time itself that is easy to miss, because it matters for everything that follows. The page time for a solar mass black hole is on the order of 10 to the 67th years. The total evaporation time for a solar mass black hole is also on the order of 10 to the 67th years. These are essentially the same number, because the information return must happen at the halfway point of the evaporation, which, when you're dealing with a curve that takes 10 to the 67th years to complete, means the information doesn't start coming back until the black hole is already almost gone. The ledger is not returned gradually a page at a time. It is held for practically the entire lifetime of the universe, or rather, for a duration that makes the current age of the universe look like the blink of an eye, and then returned in a rush at the end. For context, the universe is about 13.8 billion years old, which is roughly 10 to the 10th years. The page time for a stellar mass black hole is 10 to the 67th years. The ratio between the page time and the current age of the universe is roughly the same as the ratio between the diameter of the observable universe and the diameter of a single proton. The information is being held on timescales that make cosmic history look like a rounding error, and we know from Page's argument that it is being held. We just, for 26 years, could not figure out how. That changes in 2019, and the change comes from the last direction anyone expected. Part 4. 2 groups, 5 days, 1 answer. May 19th, 2019. Jeffrey Pennington, a postdoctoral researcher at Stanford University, posts a paper to Archive titled Entanglement Wedge Reconstruction and the Information Paradox. 5 days later, on May 24th, a team from UC Santa Barbara and the Institute for Advanced Study, Ahmed Almeri, Netta Engelhardt, Donald Marolf and Henry Maxfield, posts a different paper reaching the same conclusion via a slightly different method. 2 groups, different institutions, different framings, same result. In physics, this kind of convergence is not coincidence. It is a signal. What they had done was derive the Page curve, not from quantum information theory imposed from the outside, not from some new assumption about what happens at black hole horizons, from the geometry of the black hole itself, using a technique from quantum gravity called the gravitational path integral, extended with a tool called replica wormholes. Let me try to give you the idea without losing you in the technical machinery, because the intuition is genuinely accessible and genuinely shocking. The gravitational path integral is a way of summing up all possible geometries of spacetime to compute quantum amplitudes. It's a quantum version of asking, what are all the possible histories the universe could have had, and how do they contribute to what we observe? Normally, when physicists compute the entropy of Hawking radiation using this tool, they consider only the simplest class of geometries, the ones where the radiation is just emitted from the horizon and floats away. Those simple geometries give you Hawking's answer. The entropy rises forever. What Pennington and the Almeri group showed is that there is another class of geometries that had been assumed to be negligible. These geometries involve wormholes, connections between different copies of the spacetime in the mathematical trick being used, and they also involve a region inside the black hole called the quantum extremal island. The island is a region of spacetime behind the event horizon that, in the accounting that the island formula demands, is included in the quantum description of the radiation outside the black hole. Not as a copy, not as a holographic duplicate stored somewhere on the horizon, as the same region, counted differently by the mathematics. Before the page time, these wormhole geometries are subdominant. They contribute a tiny correction. The simple Hawking geometry wins and the entropy rises. But after the page time, something flips. The wormhole geometries take over. They become the dominant contribution to the path integral, and when you include them, the entropy turns around. It begins to fall. The page curve emerges, not from some new physics, not from some modification of quantum mechanics or general relativity, but from the geometry of the black hole itself computed in the usual way, with the full set of geometries properly included. The result was peer-reviewed, cited, extended, verified in toy models, and followed up by additional papers from Pennington, Schenker, Stanford and Yang in 2022 that sharpen the picture of what is happening inside the black hole interior. The consensus review article, written by Almeri, Hartman, Maldacena, Shagulian, and Tajdini, was published in Reviews of Modern Physics in 2021, which is the closest thing physics has to a seal of approval from the field. The mainstream has landed on this result. The page curve is derivable, the information escapes, but now we have to face the implication, because deriving the page curve is one thing. Understanding what it physically means, what is actually happening at the level of individual bits, is something else. And what it physically means is something that should make you stop and look at the room you're sitting in differently. The mechanism involves something that was, for most of the history of black hole physics, considered impossible. The interior of the black hole, the region behind the event horizon, the place that is defined by the impossibility of escape, is, after the page time, encoded in the radiation outside. The same region of space-time is, in the quantum gravitational accounting, in two places at once, not two copies, one thing counted from two different angles, and that statement taken seriously is the beginning of something much larger than a solution to a 50-year-old bet about information. Here is the key piece that made all of this possible, and it is almost unknown outside the field. A 2006 paper by Shinsei Ryu and Tadashi Takayanagi, now called the Ryu-Takayanagi formula, which showed that the area of a minimal surface in a holographic spacetime equals the entanglement entropy of a region on the boundary. This is a geometric formula for a quantum quantity. It translates entanglement, which is a property of quantum states, not of geometry, into area, which is a property of geometry, not of quantum states. Without this formula, the island calculation doesn't exist. With it, the whole thing becomes computable. Takayanagi won the Breakthrough Prize in Fundamental Physics in 2024, which is some of the best calibrated recognition physics has produced in recent years, because that formula is genuinely one of the most important results of the last 3 decades. What comes next is where the story gets truly strange. We know the information escapes, we know the curve it follows, we have the mathematics. What we do not have is a physical picture of what is happening bit by bit, letter by letter, word by word. And the reason we don't have that picture is that the picture requires us to say something very uncomfortable about where the interior of a black hole actually is. Part 5, where the interior went. I want to describe something to you, and I want you to think about it carefully, because it is the most counterintuitive thing we will cover in this video, and it is also the thing that the physics most clearly demands. Imagine a black hole. It formed from a collapsing star, and it has been evaporating via Hawking radiation for an unimaginable amount of time. The universe has grown old around it. The page time has passed, meaning more than half of its mass has evaporated, and we want to ask a simple question. Where is the interior? In the classical picture, the picture we all grew up with, the interior is inside. The event horizon is the boundary. Things that fell in are on the inside. Things that didn't are on the outside, simple, clean, geometric. Here is what the island picture says. After the page time, the interior of the black hole is encoded in the Hawking radiation outside. The same region of space-time is, in the quantum gravitational accounting, part of the description of the radiation. The interior and the radiation are not two separate quantum systems that are entangled with each other. They are the same system, described from two different angles. The way a hologram looks different when you tilt it, but it's still encoding the same information. The partition between inside and outside, the thing that made the event horizon meaningful, is not a fixed feature of the physics. It is a feature of how you are choosing to decompose the Hilbert space. And after the page time, the decomposition that gives a clean inside and a clean outside is the wrong one. This is not just philosophically uncomfortable, it is mathematically precise and physically consequential. It means that an observer outside the black hole, watching the radiation, has access to the quantum state of the interior, in principle, not practically, but in principle, through the radiation they are collecting. It means the interior is broadcasting its contents, in scrambled form, into the space around the black hole. It has been doing this since the page time, the most hidden region in the universe. The thing defined by the impossibility of escape is not actually hidden. It has a back door, and the back door is the radiation. Now this is where the AMPS firewall paradox becomes relevant, because in 2013, a year before anyone had the island picture, Joseph Polchinski and collaborators Almheiri, Marolf, and Sully, AMPS, acronym of initials, identified a devastating logical conflict hiding in the combination of these ideas. Their argument was precise. If information escapes in the radiation, and if quantum mechanics holds, then the radiation emitted early in the evaporation, and the radiation emitted late must be entangled with each other, that is required to produce a pure final state from a pure initial state, which is what unitarity demands. But the radiation emitted late is also supposed to be entangled with the interior of the black hole, as any observer falling in would expect from a smooth horizon. Quantum mechanics has a rule. A particle can be maximally entangled with only one other system at a time. This is called monogamy of entanglement. So either the late radiation is entangled with the early radiation, which is what unitarity requires, or it is entangled with the interior, which is what the equivalence principle requires. It cannot be both. Pick any two of the three principles: unitarity, equivalence principle, quantum field theory at the horizon, and the third must fail. AMPS proposed the firewall as their resolution. If unitarity holds, and if quantum field theory holds, then the equivalence principle fails. An observer falling through the event horizon is not smoothly transported into an interior region. They are vaporized at the horizon by a curtain of high-energy radiation. Einstein's most cherished insight, that a freely falling observer should feel nothing special at the horizon, breaks down. The firewall is a wall of fire at the event horizon. The island picture offers a different resolution, and it is stranger than the firewall in a way that took the field several years to fully absorb. The interior is not separate from the radiation. After the page time, there is no paradox of monogamy, because the radiation and the interior are not two separate systems competing for entanglement with each other. They are descriptions of the same system. The late radiation is entangled with the early radiation, yes, and this is also consistent with a smooth interior, because the interior and the late radiation are already the same thing in the post-page time accounting. The equivalence principle can be preserved. The firewall is not necessary. The interior still exists. It is just relocated to the outside. But here is the uncomfortable truth I promised you at the end of part 4. As of the 50-year anniversary workshop that ran through October and November of 2025 at the Simon Center for Geometry and Physics at Stony Brook, the firewall is not dead. It is a minority position. The island picture is dominant. But Samir Mathur at Ohio State University and his collaborators in the fuzzball program in string theory argue for something even more radical, that the interior doesn't exist at all, that what we call the interior is replaced by a Planck-scale tangle of stringy excitations, and the black hole is a fuzzball with no horizon in the conventional sense. This view is also consistent with the page curve. The page curve tells you the shape of the answer. It does not uniquely determine the physical picture that produces it. And then there is Kip Thorne, who remains unconvinced by any of the above. the man has not paid his half of the 1997 bet. His position, stated publicly, is that the island picture has been proved only in toy models, simplified two-dimensional gravitational theories, and has not been derived in a full, realistic four-dimensional quantum gravity. He is not wrong. That gap is real. It is one of the largest open problems in the field. The mathematics of the island calculation is rigorous within its domain. Whether that domain includes our universe is still an open question. So where does that leave us? The information escapes. The interior is connected to the exterior in a way that the classical picture of a black hole completely conceals. The geometry we thought was clean, inside, outside, horizon as boundary, is a derived description, not a fundamental one. And that word derived is the key to everything that comes next. Part 6. The ringing black hole and the theorem it confirmed. Let me bring you back to Earth for a moment, because everything I have described so far might feel like pure theory, beautiful mathematics conducted in the abstract, with no physical anchors in anything observable. I want to give you one of the most powerful physical anchors in the history of the field, because it changes the emotional register of the whole story. January 14th, 2025. Both of LIGO's interferometers, one in Hanford, Washington, and one in Livingston, Louisiana, are operating normally. Just after 8:22 in the morning Coordinated Universal Time, they register nearly identical gravitational wave signals, with parts of the signal having a signal-to-noise ratio above 10 sigma. 10 sigma means the probability of this being a noise fluctuation is so small that the number of zeros after the decimal point before you hit a 1 would fill a book. This is an event. This is two black holes colliding roughly 1 billion light-years away. The first black hole had a mass of about 33.6 times the mass of the Sun. The second had a mass of about 32.2 solar masses. They merged into a single black hole of about 62.7 solar masses, releasing the equivalent of about 3.1 solar masses as pure gravitational wave energy in a fraction of a second. Think about that. 3 entire suns worth of mass converted to ripples in space-time and radiated outward at the speed of light. And LIGO heard it from 1 billion light-years away. But here is the part that matters for our story. The signal was so clear, signal-to-noise ratio of about 77 to 80, roughly 3 to 4 times better than the previous record, that for the first time scientists could resolve 2 distinct quasi-normal modes in the ring-down phase. The ring-down is what happens after 2 black holes merge. The resulting object, initially distorted and asymmetric, rings like a bell as it settles into its final Kerr shape. Different modes of ringing have different frequencies and different decay times, and general relativity predicts exactly what those frequencies and decay times should be for a Kerr black hole of a given mass and spin. GW 25114 matched those predictions to within a few percent. This is black hole spectroscopy. This is literally listening to a black hole's ringing tones and using them to read off its properties, the way you might identify a particular bell by its pitch and overtones. And what the spectrum said was, this is a Kerr black hole, exactly as described. The math is right. The geometry is real. The result also confirmed Stephen Hawking's area theorem from 1971. The area of the event horizon of the final merged black hole was larger than the combined area of the 2 initial black holes. It had to be. The area theorem says that the total horizon area of all black holes can never decrease. This was confirmed directly at 4.1 sigma significance, the first definitive observational confirmation. The same Hawking, whose information calculation was wrong enough to lose a famous bet, had his area theorem confirmed to higher precision than ever before by the loudest gravitational wave signal ever detected. There is something almost narratively satisfying about that, and also something that deepens the paradox rather than resolving it. Because here is what GW 25114 tells us. The outside of a black hole, its mass, its spin, its ring-down signature, its adherence to the area theorem, is exactly what general relativity says it is. The exterior is understood. The Kerr metric is correct. general relativity works beautifully at black hole scales. And yet the question of what is happening with the information inside, the question of how the interior is encoded in the exterior, and what that encoding means for the geometry of space, that question is not answered by GW 25114. It is sharpened by it. The more precisely we measure the outside, the more the inside demands explanation. This is not an accident. The information paradox was always a conflict between the very precise classical description of the exterior, the event horizon, the Kerr metric, the area theorem, and the quantum mechanical requirements of the interior. What GW 25114 does is make the exterior description so precise and so confirmed that there is nowhere left to hide an easy answer. The outside is classical and exact. The inside is quantum and strange. The gap between them is where all the interesting physics lives. And speaking of interesting physics, let's talk about the tool that made the 2019 calculation possible, and the principle behind it that makes the whole story much larger than a black hole problem. Because the island picture did not arrive from nowhere. It arrived from a direction that had been building since 1993, when a Dutch physicist made a proposal that the entire field thought was probably wrong. Part 7. The principle that sounds absurd. Gerard 't Hooft won the Nobel Prize in Physics in 1999 for work on the structure of particle physics. He is one of the most careful and respected theorists of the 20th century. So when 't Hooft, in 1993, proposed something that sounded like a science fiction premise, the field listened, even as it struggled to believe him. His proposal was this: the maximum information content of any region of space is proportional to the surface area of that region's boundary, not its volume. Take a sphere of any size, anywhere in space. The maximum number of bits of information that can be contained inside that sphere is proportional to the area of the sphere's surface, measured in Planck units, not the volume, the area. This is the opposite of every intuition about information storage. A library stores more books when you add more shelves, more volume, more information. Every system we know of scales with volume. Information density is a property of bulk, not surface. 't Hooft said, for gravity, this is wrong. The maximum information content of any region is a surface phenomenon. The interior is, in some sense, redundant. Everything inside is already encoded on the boundary. The reason this is not completely crazy is Bekenstein's black hole entropy result. If you want to pack the maximum possible information into the smallest possible space, you make a black hole. Black holes are the most information-dense objects in the universe, and the entropy of a black hole, which is proportional to the information it encodes, goes as the area of the event horizon, not the volume inside. Bekenstein found this in 1973 and didn't fully know what to do with it. 't Hooft in 1993 said, "This isn't a quirk of black holes, this is a property of space itself, the holographic principle." Leonard Susskind took 't Hooft's proposal seriously in 1995 and connected it to string theory, developing it into a framework he called the holographic principle. The three-dimensional universe we experience may be a projection of information stored on a two-dimensional surface, the way a hologram on a credit card encodes a three-dimensional image on a flat film. The comparison to a hologram is not metaphorical. It is structurally precise. The information on the boundary encodes the physics in the bulk, just as the interference pattern on a holographic film encodes the three-dimensional object it represents. Then, in 1997, Juan Maldacena published the paper that gave all of this its first concrete mathematical realization, the ADS/CFT correspondence. Anti-de Sitter space, a particular kind of space-time with a negative cosmological constant that curves inward, is dual to a conformal field theory living on its four-dimensional boundary. Two theories, different number of dimensions, different physical content on the surface, mathematically identical, exact. Every calculation you do in the bulk gravity theory has a corresponding calculation in the boundary field theory, and vice versa. You can translate between them. Maldacena's paper now has over 25,000 citations. That is the most cited paper in the history of theoretical physics, not the most cited paper in string theory. the most cited paper in all of theoretical physics. The field voted with its feet on whether this result was important. But here is the problem that matters for the information paradox, and for the question of whether any of this applies to the universe we actually live in. Anti-de Sitter space is not our universe. Our universe has a positive cosmological constant. It is expanding, accelerating, and asymptotically approaching a de Sitter geometry, a space-time that curves outward rather than inward. The two types of space-time are about as different geometrically as you can get while still calling them both space-times, and there is no proven ADS/CFT style holographic correspondence for de Sitter space. This is not a footnote, this is one of the largest open problems in theoretical physics. The island calculation uses ADS/CFT machinery, specifically the Reuter-Kayanergi formula, which was derived in the ADS/CFT context. The calculation works, it gives the right page curve, but it was done in a space-time that is not the universe we live in. The extension to de Sitter space, the extension to our universe, has not been proven. Leonard Susskind published a paper in 2023 attempting to make de Sitter holography precise, using an observer-dependent framework where time reversal is a gauge symmetry. It is controversial, it is unresolved, it is one of the most important papers waiting to be proven or disproven in the field right now. So the holographic principle, the idea that the universe we experience may be a projection from a lower dimensional surface, is on extremely firm mathematical footing in the wrong space-time, and on speculative but compelling physical footing in the right one. This is not a reason to dismiss it. It is a reason to understand it as a frontier, and the frontier matters because the holographic principle is the context in which ER equals EPR, the strangest idea this video will cover, makes sense. Part 8. Einstein's Two Children. 1935 was a remarkable year for Albert Einstein, and not in a way he would have appreciated. He published 2 papers that year on 2 completely separate topics, with 2 completely different sets of collaborators. He thought both results were curiosities that nature would probably never realize. He spent the rest of his life trying to get rid of at least one of them. And in 2013, Juan Maldacena and Leonard Susskind published a paper arguing that those 2 results from 1935 were, in fact, the same result. The first paper, written with Nathan Rosen, described what we now call a wormhole. They found a solution to the Einstein field equations in which 2 distant regions of space-time are connected by a tunnel, a bridge through a higher dimensional space, connecting what look like 2 separate black holes from the outside. Einstein and Rosen thought it was a mathematical artifact. They did not think wormholes were physically real. The paper was filed under interesting but probably irrelevant. The second paper, written with Boris Podolsky and Rosen, different Rosen, same year, remarkable that he had 2 papers with a different co-author who had the same name, introduced what we now call quantum entanglement. 2 particles interact and separate. Their quantum states become correlated in a way that persists regardless of the distance between them. Measure one, and you instantly know something about the other, no matter how far apart they are. Einstein hated this. He called it spooky action at a distance. He thought it proved quantum mechanics was incomplete, that there had to be hidden variables, some underlying classical description, that made the correlation sensible. He spent years trying to get rid of entanglement as a fundamental feature of reality. He failed. John Bell proved in 1964 that no hidden variable theory could reproduce all the predictions of quantum mechanics, and experiments confirmed Bell's theorem beyond reasonable doubt. The ER paper, wormholes, the EPR paper, entanglement, both published in 1935, both considered by Einstein to be signs that the relevant theory was incomplete or unphysical. And in 2013, Maldacena and Susskind wrote a 4-letter equation that connected them, ER equals EPR. The proposal is this: wormholes and entanglement are not 2 different phenomena. They are 2 descriptions of the same phenomenon, viewed from different theoretical angles. Every entangled pair of particles is connected by a microscopic, non-traversable Einstein-Rosen bridge. Not metaphorically, physically. The entanglement is the wormhole. The wormhole is the entanglement. The reason you cannot use entanglement to send information faster than light is that the wormhole it corresponds to is non-traversable. Nothing can pass through it. The reason the wormhole is non-traversable is that the entanglement cannot be used for signaling. They are the same constraint, the same physics, the same thing. This is ER equals EPR. And if it is right, then the entanglement structure of the quantum vacuum, the vast seething network of correlations between quantum fields at every point in space, is the geometric stitching that holds spacetime together. The space between things is not empty. It is full of entanglement, and that entanglement is, in the language of general relativity, a network of Planck-scale wormholes so tiny and so numerous that they average out into the smooth, continuous geometry we experience as space. Mark van Ramsdonk put this into the sharpest possible form in his 2010 paper. Take two entangled regions of space-time, slowly reduce the entanglement between them. As the entanglement decreases, the geometric distance between the regions grows. When entanglement reaches zero, the regions are infinitely far apart, causally disconnected in different universes. Reverse the process, increase entanglement, and the regions approach each other. At a critical density of entanglement, they merge into a single connected space-time. Geometry, in this picture, is the readout of entanglement. Distance is what entanglement looks like when you stop paying attention to the individual qubits. Space is not a background. Space is a property of the quantum state. And now go back to the information paradox. The reason the information escapes from a black hole in the island picture is that as Hawking radiation accumulates, the radiation becomes increasingly entangled with the interior. That growing entanglement is, in the ER equals EPR language, a growing wormhole connecting the radiation to the interior. After the page time, the wormhole is large enough that the interior is effectively encoded in the radiation, not because anything has passed through the horizon, but because the horizon is no longer the boundary between two separate quantum systems. The entanglement has made them one. There is observational evidence for this picture, though it is indirect and contested. The Gauss-Jeffress-Wald protocol, published in 2017, showed theoretically that by injecting negative energy into a wormhole, which corresponds to creating a particular pattern of quantum interactions between the two ends, you can make a non-traversable wormhole temporarily traversable. In 2022, a team at Caltech led by Maria Spiropoulou demonstrated a wormhole-like quantum teleportation effect on Google's Sycamore quantum processor, using a model called the Sachdev-Yekitaev model, which is a holographic toy model that has an approximate dual description as a wormhole. The interpretation of this experiment is still being actively debated. Some physicists argued it was a simulation of holographic physics rather than the thing itself, but it demonstrated that the SYK model, the same toy model that underlies many of the island calculations, behaves as ER equals EPR predicts. Einstein wrote both the ER paper and the EPR paper in 1935. He disliked both results for the same underlying reason. They both implied that the universe is stranger and more non-local than classical intuition suggests. He was right that they were strange. He was wrong that they were signs of incompleteness. They were, it turns out, two chapters of the same story, and the story they were telling is that the space between things is not a fixed background. It is made of something, and what it is made of is the quiet, persistent, irreducible fact that different parts of the universe know about each other. Part 9. The Conspiracy Theories and Why the Real Answer is Weirder. I want to spend some time on the fringe interpretations of this story, and I want to be upfront about why, because it is genuinely instructive, and not in the way that usually gets said about fringe theories. The usual move is to debunk them and move on. That's not what we're doing here. Because some of these ideas are wrong in ways that actually point toward the real physics. And some of them, and this is the part that should make you sit up a little, are wrong in directions that are genuinely less strange than the correct answer. The truth, in this case, is weirder than the conspiracy theory. That doesn't happen often. When it does, it's worth paying attention to. So let's go through them, one by one, and let's be honest about what each one gets right, what it gets wrong, and why the distinction matters. The portal theory. The one that comes up most often, in comment sections, in late-night Reddit threads, in the kind of YouTube videos that use a lot of red circles, is that black holes are portals to other universes. It gets filed under science fiction. It gets dismissed as crackpot speculation. And I understand why, because the way it usually gets presented is crackpot speculation. But the underlying idea has a pedigree that most people don't know about, and it's worth taking seriously for a moment before we explain why it doesn't work the way people think. Here's the respectable version. In loop quantum gravity, which is one of the serious peer-reviewed attempts to reconcile general relativity with quantum mechanics, there is a class of solutions called bouncing geometries. The Penrose-Bonanno-Modesto model specifically replaces the singularity at the centre of a black hole with something called a quantum bounce. Instead of matter collapsing to a point of infinite density where the equations break down and physics throws up its hands, the matter bounces. The compression reaches a maximum governed by quantum geometry at the Planck scale, and then the collapse reverses. And in the mathematical structure of that solution, the interior of the black hole connects, through that bounce, to the interior of what's called a white hole, in a different region of space-time. Possibly a region so disconnected from ours that different universe is the most honest way to describe it. And then there's the Kerr metric, the exact solution to Einstein's field equations for a rotating black hole. If you extend it maximally, if you follow the mathematics as far as it will go, without imposing any artificial boundaries, it contains topological structures that connect to other space-time regions. Ring singularities, closed time-like curves, passages through. The geometry is right there in the equations. Einstein himself found some of this and didn't know what to make of it. So the portal idea is not invented from nothing. The topology exists in the mathematics. What the physics forbids is not the topology but the traversal, and the reasons it forbids traversal are not subtle. The tidal forces near the singularity of a realistic black hole, a black hole formed from a collapsing star, not a mathematical idealization, exceed the structural limits of any known matter by so many orders of magnitude that the question of where you would emerge is completely academic, because you would not emerge as anything recognizable. You wouldn't emerge as ash. You wouldn't emerge as radiation. You would emerge as a smear of quantum states that used to be you, separated from each other by distances that have no meaning in any coordinate system you would care about. The portal doesn't kill you. It just means that the concept of you stops applying somewhere in the approach. But here is where it gets interesting, and I mean genuinely interesting, not just interesting for a YouTube video. Interesting. The island picture, the result from 2019 that is the centerpiece of this whole story, says that the interior of a black hole is connected to the exterior radiation, not geometrically, not through a tube in space you could theoretically navigate if you were made of something indestructible. The connection is quantum informational. The information about what fell into the black hole passes from the interior to the exterior through the accumulated entanglement of Hawking radiation, through correlations between photons that have been drifting away from the black hole for billions of years. The channel is real. The portal is real. It's just that the portal is made of entanglement, not geometry. It is not a door you can walk through. It is a channel through which information flows, impossibly slowly, scrambled beyond any practical decoding, but present. The fringe intuition caught the right topology. It just got the mechanism completely wrong. The universe does connect the inside to the outside of a black hole. It just does it in a way that makes wormholes look almost quaint by comparison. The simulation argument. This is the one I want to spend the most time on, because it is simultaneously the most common misreading of holography and the most illuminating one. It goes like this. The holographic principle says the universe is a hologram. A hologram is a projection. A projection requires a projector. A projector is a computer. Therefore, we are in a simulation. Elon Musk has said some version of this publicly. It gets cited in philosophy papers. It has a kind of intellectual respectability that the portal theory doesn't quite achieve. And I want to be clear about something before I explain why it's wrong. The people making this argument are reaching for something real. They are sensing correctly that the holographic principle implies something radical about the nature of the three-dimensional reality we experience. They're just drawing the wrong conclusion from a genuine insight. Here's what holography actually says, in the technical sense developed by 't Hooft in 1993, Susskind in 1995, and Maldacena in 1997. The information content of any region of space is bounded by the area of that region's boundary, measured in Planck units, not the volume, the area. What this means, concretely, is that the maximum number of independent facts you could ever need to fully describe everything happening inside a given sphere is proportional to the surface of that sphere, not to the space inside it. The interior, in some deep sense, is not adding as much information as you'd expect. The three dimensions feel real. They are real, measurably, concretely, causally real in every way that matters for daily life. But they may not be the most fundamental description of what's here. Here is what holography does not say. It says nothing about an external computer. It says nothing about a simulator. It says nothing about anything outside the universe running a program that generates the universe's output. The bound is intrinsic to the physics of this universe. It is a property of how gravity and quantum mechanics interact at the Planck scale. There is no implied external hardware. There is no implied programmer. The holographic principle is not a simulation argument. It is, if anything, the opposite of a simulation argument, because a simulation argument assumes the universe needs an outside to explain its inside, and holography is a statement entirely about the inside, derived from the inside, with no reference to anything external at all. But, and here's where I want you to stay with me for a moment, holography does imply something that is, I would argue, stranger than the simulation argument. Because the simulation argument just says someone built the universe in a computer. That's a big claim, but it's a structurally familiar one. We know what computers are. We know what simulations are. We run them. The claim is bold, but the concept is comprehensible. What holography actually implies is that the three dimensions of space you experience, the depth, the distance, the sense that you're inside a volume rather than on a surface, are derived properties. They emerge from something lower dimensional. The dimension count of the universe may be, in some precise mathematical sense, cosmetic. Not fake, not illusory, but not fundamental. The universe is, in the language of the mathematics, shallower than it looks. And that shallowness has no analogy in any computer architecture that has ever been conceived, because every computer architecture we have ever imagined exists inside three-dimensional space, and takes that space for granted. Holography is not saying the universe is like a simulation. It is saying the universe has a structure that makes the concept of simulation, which requires an outside and an inside, difficult to even formulate clearly. The simulation argument reaches for the right thing and lands in the wrong place. The right thing it's reaching for is the intuition that something about three-dimensional reality is not the whole story. That intuition is correct. The conclusion it draws from that intuition, that someone is running the program, is a category error. The strangeness is not that there's a programmer. The strangeness is that there may be no fact of the matter about how many dimensions the universe has at the most fundamental level, which is a much harder thing to sit with than the simulation argument, because the simulation argument at least gives you someone to imagine, Kip Thorne, the last holdout. Then there is Kip Thorne, and I want to be careful here because Thorne is not a conspiracy theorist and he is not a crank. He is one of the architects of modern gravitational physics. He shared the Nobel Prize in 2017 for the detection of gravitational waves. He has more credibility in this field than almost anyone alive, and as of 2026, he is the only party to the original 1997 bet who has not conceded. His half of the encyclopedia has never been paid. His position is worth understanding carefully, because it is not the position you might expect from someone holding out. He is not saying information is definitely lost. He is not defending Hawking's original conclusion. His position is narrower and more precise than that, and it is, and I say this as someone who finds the island picture extremely compelling, not wrong. His argument is that the island calculation has been proven only in toy models, specifically in something called Jacutitle-Boym gravity, which is a two-dimensional dilaton gravity theory. JT gravity is a powerful and mathematically tractable model. It has taught physicists an enormous amount about quantum gravity, in a regime where the full path integral is actually computable. But it is not the universe. It is a two-dimensional simplification of the universe, and the extension of the island result to a full, realistic, four-dimensional theory of quantum gravity, the kind that would describe an actual black hole in our actual universe, has not been proven. The field's centre of gravity has moved well past Thorne on this. The consensus, as of the Simon Center workshop in late 2025, is that the island picture is almost certainly correct in principle and will generalize. But consensus is not proof. And Thorne is right that the gap between works in JT gravity and works in four-dimensional quantum gravity in our universe is a real gap, not a technical footnote. What makes his position interesting, genuinely interesting, not just diplomatically interesting, is what it reveals about where physics actually is right now. The island picture is the consensus, but we are in the middle of a revolution, not after one, and the difference matters. After a revolution, the new picture is established and the community fills in details. In the middle of one, the new picture has overwhelming evidence in its favour and a handful of crucial steps still missing. Thorne is standing at one of those missing steps and declining to jump over it. You can disagree with his conclusion while respecting the precision of his objection. I do. The CERN black hole panic. Every few years, when CERN announces it's running the LHC at higher energies, a particular story cycles back through social media. The concern that the collider might create a black hole and destroy the Earth. I mention it not because it is credible, it isn't, and the reasons it isn't are well established and unambiguous, but because the underlying physics connects to something genuinely fascinating that almost nobody talks about. Certain theoretical models with extra spatial dimensions, the Randall-Sundrum model, the ADD model, predicted that if the fundamental Planck scale associated with those extra dimensions was low enough, the LHC might produce microscopic black holes at TV energy scales. The LHC has been running for well over a decade at the energies these models specified. It has found no signature of microscopic black holes, which means either the extra dimension models are wrong, or the Planck scale is higher than they predicted, or both. The Earth destruction concern was never credible, because any black hole produced at those energies would have been so microscopic and so short-lived that it would have evaporated essentially instantaneously. The evaporation timescale for a black hole of that mass is roughly 10 to the minus 28 seconds. That is 100 million trillion times shorter than the time it takes light to cross a single proton. But here is the thing that I find quietly wonderful about this. If those microscopic black holes had been created and had evaporated in 10 to the minus 28 seconds, if that entire process had played out inside the detector, before a single electronics gate could open, the information paradox would have applied to them. The island formula, if it's correct, would have had to work on timescales shorter than a nanosecond. We would have had a tabletop test of the deepest unsolved problem in theoretical physics, running millions of times per second inside a particle detector in Switzerland, and nobody would have known it was happening, because the entire experiment, the black hole forming, the information scrambling, the page curve playing out, the final evaporation, would have been over before any instrument in the history of technology could have registered a single event. The universe really does have a sense of humour about these things. The suppression myth. The last fringe narrative worth addressing is the claim that Hawking was somehow suppressed, or that his findings were hidden or managed by scientific institutions. I want to deal with this one directly, because it is not just wrong, it runs opposite to the documented record of his career in almost every detail. Hawking changed his public position on the information paradox on international television in 2004 in front of a room full of his peers, handing over a baseball encyclopedia as payment for a lost bet. He published scientific papers continuously, right up to 2018, the year he died. He had complete freedom to say whatever the evidence led him to say, and he exercised that freedom repeatedly and publicly on one of the most contested questions in his field. The suppression narrative requires you to believe that a man who changed his position in front of cameras in real time, surrounded by scientists who disagreed with him, was somehow being controlled by the very establishment he was publicly disagreeing with. The logical structure of that argument collapses the moment you examine it. What is actually true, and this is more interesting than any suppression story, is that Hawking was probably still not completely right even in his 2004 concession. The proof he presented in Dublin was not accepted by the room. The physicists who had spent their careers on this problem listened to his argument and were not convinced. John Preskill accepted the encyclopedia that afternoon, and later admitted publicly that he didn't think Hawking had solved it. Kip Thorne refused to concede at all. The question that Hawking devoted 30 years of his career to was partially answered 6 years after his death, by a generation of physicists he trained and influenced, using mathematical tools that were developed after he formed his original position. He was right that information is preserved. He was right that Preskill was right. He was wrong about the mechanism. His calculation from 1974 was not wrong in its mathematics. It was wrong in an assumption so subtle that it took 45 years to locate and name. That is not suppression. That is not conspiracy. That is what science actually looks like when it's working. Slow, contested, occasionally humbling, and ultimately honest about what it doesn't know. The universe kept its ledger. It just took us a while to find the page it was written on. Part 10. Space is made of something else. We've arrived at the part of the story that I think is the most important and the hardest to articulate without sounding like you have lost the thread of physics and wandered into philosophy. And I want to stop right here and address that directly, because the moment this starts sounding like philosophy, like speculation, like someone connecting dots that don't actually connect, I want you to push back. Hold me to it. Because what I'm about to describe is not philosophy. It is not metaphor. It is not a poetic interpretation of difficult mathematics that someone thought would make a good video. It is the destination toward which every single result described in this video has been pointing, derived from the same equations, confirmed in the same peer-reviewed literature by the same community of physicists who gave us the page curve and the island formula and the Ryuta-Kayanagi result. The information paradox was the doorway. What follows is the house, and the house is stranger than anything the doorway suggested. Space-time is not fundamental. Let me say that plainly, and then let me say it again, because it is easy to hear and considerably harder to absorb. Space-time, the four-dimensional continuum of 3 space dimensions plus time, the stage on which every physical event in the history of the universe has played out, the thing that general relativity describes with such extraordinary precision that we can use it to navigate spacecraft to the outer planets, is not the most fundamental layer of reality. It is a derived property. It is what something else looks like when you zoom out far enough to stop seeing the individual pieces. It is an emergent description, a coarse-grained average, a readout. And what it is a readout of, what the individual pieces actually are, beneath the geometry, is entanglement. I want to give you a moment with that, because rushing past it would be a disservice to how genuinely strange it is. We are not saying space-time is approximate, the way Newtonian mechanics is approximate, correct at low velocities, wrong at high ones, but still a decent description of the territory. We are saying space-time is derived. The way temperature is derived from the average kinetic energy of molecules. Temperature is real. It is measurable. You can burn your hand on something hot. But temperature is not fundamental. It is what the motion of enormous numbers of individual molecules looks like when you stop tracking each one and just ask about the average. Space-time, in the picture that the mathematics of the last 30 years has been building, is like temperature, real, measurable, causally effective, but not the bottom of the stack. The bottom of the stack is something else. And that something else is the pattern of quantum correlations, the entanglement between the degrees of freedom that make up the universe at its most fundamental level. The program and the people building it. This is called the Emergent Spacetime Program. It is associated primarily with Mark van Ramsdonk at the University of British Columbia and Brian Swingle at the University of Maryland, though the community of researchers contributing to it now spans dozens of institutions and several overlapping fields: quantum information theory, condensed matter physics, string theory, and quantum gravity, which do not normally share a vocabulary or a whiteboard. The fact that they are converging on the same picture from different directions is one of the most significant signals in contemporary theoretical physics. The core claim of the program is this: you do not start with space-time and add quantum fields to it, and then notice that entanglement appears as a byproduct. You start with entanglement, with a quantum system whose primary structure is correlations between its parts, and space-time geometry emerges from the pattern of those correlations, the distances between things, the curvature of space, the number of dimensions you can move through, all of it derived, all of it secondary, all of it what the entanglement looks like when you average over the individual quantum degrees of freedom and ask what effective geometry they produce. This is a complete inversion of how physics has thought about space for 300 years. Since Newton, space has been the container, the thing that other things are in, the background. First Newton's absolute space, then Einstein's dynamical space-time that bends and curves in response to mass and energy. But still, in both cases, the space is prior. The space is the stage. Things happen on it. The Emergent Spacetime Program says the stage is not prior. The stage is an output. The stage is what you get when you look at the entanglement from far enough away that you stop seeing the qubits and start seeing the geometry they collectively produce. Swingle's result and why it should unsettle you. Brian Swingle made this concrete in 2012 in a paper that I think deserves to be far more widely known than it is. What Swingle showed is almost disturbingly clean in the way that the best results in theoretical physics are clean, where you follow the logic and arrive somewhere that feels inevitable and impossible at the same time. He started with a class of quantum many-body systems. These are the kinds of systems that condensed matter physicists study, large collections of quantum particles whose states are correlated with each other in specific ways. Electrons in a superconductor, atoms in a quantum magnet. Systems where the interesting physics lives in the correlations between parts, not in the individual parts themselves. These systems have entanglement structures, patterns of quantum correlation that can be mapped out and analysed. Swingle showed that the entanglement structure of a specific class of these systems can be organised into a mathematical object called a tensor network. A tensor network is essentially a graph, a collection of nodes, each representing a quantum state, connected by links that represent entanglement relationships. Different patterns of connection produce different tensor networks, and Swingle showed that the specific tensor network corresponding to the entanglement structure of a particular class of quantum many-body systems, called the mirror network, which stands for multi-scale entanglement renormalization ansatz, a name that is considerably less intimidating than it sounds, exactly reproduces the geometry of anti-de Sitter space. Let me be precise about what that means, because it is easy to hear reproduces the geometry and think it means looks a bit like. It does not mean looks a bit like. It means that the spatial distance between 2 points in the bulk spacetime corresponds, precisely and quantitatively, to a measure of how many entanglement bonds you have to cross in the tensor network to get from one boundary region to another. Distance in the bulk geometry is entanglement, counted. The curvature of the space is encoded in the connectivity of the network. The shape of the geometry on one side of the equation is the entanglement structure on the other side. This is not an analogy. This is a mathematical identity. Two descriptions of the same thing. You can take a quantum system that has no spatial description no coordinates, no metric, no notion of here versus there, and read the geometry of a three-dimensional curved space-time directly off its pattern of correlations. The space was in the entanglement the whole time. The entanglement was the space, what this has to do with black holes. And now I want to bring this back to the information paradox, because this is where everything in this video converges. Because the information paradox was never really about black holes. I know that sounds like a strange thing to say after spending this much time on black holes, but black holes were the laboratory. They were the extreme case, the place where the conflict between general relativity and quantum mechanics becomes so severe that it can no longer be ignored, papered over, or deferred to a future theory. The actual question hiding behind the question of where the information goes is this. If the geometry of space-time emerges from entanglement, what happens when the entanglement reorganizes? Think about what happens as a black hole evaporates. The black hole and the Hawking radiation outside it form a single quantum system. As the evaporation proceeds, the entanglement between the interior and the exterior radiation grows. It builds up over time, and then, at the page time, after more than half the black hole's mass has evaporated, something shifts. The entanglement structure of the combined system reorganizes. The island appears. The interior of the black hole, in the quantum informational accounting, becomes encoded in the radiation outside. The partition between inside and outside, the thing that made the event horizon meaningful as a boundary, dissolves. Now here is what the emergent spacetime picture adds to this. When we say the partition dissolves, we are not saying something moved inside a fixed spacetime. We are not saying the information teleported from one location to another, while the geometry stayed the same. We are saying the entanglement that built the geometry, the entanglement that defined the inside as geometrically separate from the outside, reorganized into a different pattern. And when the entanglement reorganizes, the geometry reorganizes with it. Because the geometry was always the entanglement, described at a larger scale. The inside and the outside are no longer geometrically separate after the page time because the quantum correlations that constructed that geometric separation have rearranged themselves into something else. The stage has changed, not because something happened on the stage, because the entanglement that the stage was made of evolved. This is why the island picture is not just a resolution of the information paradox. It is a demonstration, a concrete, mathematically explicit demonstration that the geometry of space-time is not a fixed background. It responds to quantum information dynamics. It reorganizes when the quantum state of the system evolves in ways that change the entanglement structure. The stage, in the deepest sense, is an output, a derived description of the quantum state. And quantum states evolve, and when they evolve in the specific way that evaporating black holes evolve, the geometry of space-time changes in ways that the classical picture, the picture of a fixed, smooth, continuous space-time with a definite inside and a definite outside, simply cannot accommodate. Van Ramsdonk's thought experiment. Mark Van Ramsdonk put this into its sharpest possible form in a 2010 paper that the journal he submitted it to initially rejected because the referee thought the conclusion was too radical. He was right that the conclusion was radical. He was wrong to reject it. Van Ramsdonk's argument was a thought experiment. Take two entangled regions of a quantum system, two groups of degrees of freedom that share quantum correlations. In the holographic picture, these two regions are connected by a geometry. Now slowly reduce the entanglement between them. Dial it down, step by step, towards zero. What happens to the geometry? The geometry stretches. The two regions move apart. The spatial distance between them grows as the entanglement decreases. And when the entanglement reaches zero, when the two regions are completely unentangled, sharing no quantum correlations at all, the geometry separating them becomes infinite. The two regions are in causally disconnected spacetimes. They are, in the only sense that matters for physics, in different universes. Now run it in reverse. Start with two separate unentangled regions. Begin adding entanglement between them. They approach each other geometrically. The distance shrinks. At a critical density of entanglement, they merge into a single connected spacetime. Space in this picture is literally woven from entanglement. The connectivity of the universe, the fact that this point in space and that point in space are part of the same geometry, reachable from each other by a continuous path, is a statement about quantum correlations, not about a fixed background. Geometry is what entanglement looks like at the scale where you stop seeing individual qubits, disconnect the qubits, remove the correlations, and the geometry falls apart. This is not a metaphor. Van Ramsdonk was not saying it is useful to think of space as being like entanglement. He was saying, in precise mathematical terms, that in the context of ADS/CFT, the geometry of the bulk spacetime is the entanglement structure of the boundary theory. One thing, two descriptions. The singularity bypassed now. What does all of this mean for the singularity? The singularity at the center of every classical black hole, the point where density becomes infinite, curvature becomes infinite, tidal forces become infinite, and the equations of general relativity simply stop producing finite answers, has not been resolved by the island picture. And I want to be honest about that, because it would be easy to imply that the emergent spacetime program ties up every loose end. It doesn't. The singularity is still there. We still don't know what it is. We still don't have a complete theory that replaces the infinite density with something finite and physically meaningful. What the island picture has done is bypass the singularity. And that is, depending on your temperament, either reassuring or deeply alarming. Here is what bypass means in this context. The island calculation works without needing to know what happens at the singularity. The information escapes through the entanglement wormhole connection, through the reorganization of the quantum state, before the singularity is reached in the quantum accounting. Whatever is at the center of a black hole, a Planck-scale region of fluctuating quantum geometry, a loop quantum gravity bounce into a new universe, a fuzzball of stringy excitations with no smooth interior at all, the information paradox does not depend on it. The resolution works regardless. The mathematics found a way around the most violent and poorly understood feature of classical black holes, and it did so with a kind of elegant indifference that should make anyone who thinks carefully about it a little nervous. Because what it means is that the calculation that resolved a 50-year paradox did so without ever looking directly at the thing that created the paradox in the first place. The singularity is still in the room. We just found a way to answer the question without opening the door. And the question of what is behind that door, what is actually happening at the center of a black hole at the Planck scale, where quantum gravity is not a correction but the entire story, remains the deepest unsolved problem in fundamental physics, not because we haven't tried. Because every tool we have developed to answer it has so far found a way to go around it instead. The universe, it turns out, is very good at hiding its sharpest edges. The singularity is the sharpest edge we know of, and the mathematics of emergent spacetime, for all its extraordinary power, has so far preferred to walk around it rather than through it. That preference itself is a clue. We just don't know yet what it's a clue to. Part 11. The 50-year workshop and what is still missing. October 6th, 2025. Stony Brook, New York. A university campus on the North Shore of Long Island, about an hour outside Manhattan, that most people outside of theoretical physics have never heard of. The Simon Center for Geometry and Physics, funded by the mathematician and hedge fund billionaire Jim Simons, who understood before most people that the boundary between pure mathematics and fundamental physics was not a boundary at all, hosted a 6-week workshop with a title that tells you exactly how seriously the field takes its own history. 50 years of the black hole information paradox. 50 years. The occasion was the anniversary of Hawking's 1975 paper formally establishing Hawking radiation and the thermodynamic framework around it. The paradox the paper implied had been the central unsolved problem in theoretical physics for half a century. And the gathering that assembled at Stony Brook to mark that anniversary was, by the accounts of people who were there, one of the most unusual scientific meetings in recent memory, not because of what was agreed upon, but because of who was in the room and how different their starting points were. String theorists, loop quantum gravity researchers, quantum information theorists, holographic entanglement specialists. These are communities that publish in different journals, cite different bodies of literature, use different mathematical tools, and, this is the part that matters, have genuinely different intuitions about what a solution to the information paradox should look like. As the organisers noted explicitly in the workshop description, these communities do not typically interact very much. They arrived at Stony Brook with different vocabularies, different frameworks, and in some cases fundamentally different views on whether the paradox had already been resolved or was still wide open. What emerged from 6 weeks of that conversation was more nuanced than the popular science coverage of the island result would suggest. And I think that nuance is worth conveying carefully, because physics done right is always more interesting than physics done triumphantly. So let me give you an honest accounting of where the field actually stands, what is agreed upon, what is genuinely contested, and what remains so open that calling it a frontier understates how much territory is still unexplored. What the room agrees on. Let's start with the consensus, because it is real and it is significant. Across all the communities represented at Stony Brook, despite the different vocabularies and the different tools and the different instincts, there was broad agreement on a core set of propositions. Information is preserved. Hawking's 1976 conclusion that black hole evaporation causes pure quantum states to evolve into mixed states, that information is genuinely destroyed, is wrong. The universe does not shred its ledger. The Page curve is the correct shape of the entropy of Hawking radiation over the lifetime of an evaporating black hole. The entropy rises, turns around at the Page time, and falls back to its initial value as the evaporation completes. The island and replica wormhole calculation is the leading candidate explanation for why and how this happens. And holography, the idea that the information content of any region of space is bounded by the area of its boundary, and that a lower dimensional description exists for any higher dimensional volume, is probably true in some form. These propositions command broad consensus. The consensus has grown noticeably stronger over the 5 years since the 2019 papers. Physicists who were skeptical in 2019, or who reserved judgment while waiting for follow-up work, have largely moved toward the island picture as additional results have come in, and as the framework has proved robust across different model setups. The sociology of the field, to use the term Hawking's own Dublin concession shifted, has settled into a new position. The information escapes. The Page curve is right. The island formula is how you compute it. That is the agreement. And it is not a small agreement. For a field that spent 50 years unable to prove which side of a fundamental question was correct, arriving at this level of consensus on this set of propositions represents a genuine shift in the state of knowledge. The four-dimensional gap. But the disagreement is real too, and I want to be specific about it rather than waving at it vaguely, because the specific shape of what remains unproven matters a great deal for how seriously you should take the island picture as a description of our actual universe. The central technical disagreement at Stony Brook was about generalization. The island calculation was derived in its cleanest and most rigorous form in a two-dimensional Dilaton gravity theory called Jaccue-Teitel-Bohm gravity, JT gravity for short. JT gravity is a powerful tool precisely because it is solvable. You can compute the full gravitational path integral in JT gravity. You can sum over all the relevant geometries exactly, without approximations, and get a definitive answer. That is an extraordinarily rare property in quantum gravity, where exact calculations are almost never available. The problem is that JT gravity is not the universe. It is a two-dimensional toy model that captures certain features of near-extremal black holes that are almost at the limit of maximal rotation or charge. But it is a simplification so severe that calling it a model of our universe requires several leaps of faith stacked on top of each other. The island result has been extended beyond JT gravity, to higher dimensional models, to setups with black holes coupled to external radiation baths, to various configurations where the geometry is more realistic, and in each of these extensions the page curve comes out, the island formula keeps working, the information keeps escaping. But the extension to a fully realistic black hole in four-dimensional spacetime, the kind of black hole that actually exists in our universe, formed from a collapsing star, embedded in a four-dimensional spacetime with all the degrees of freedom that implies, has not been proven. The full gravitational path integral in four-dimensional quantum gravity cannot currently be computed because a complete calculable theory of four-dimensional quantum gravity does not exist. We do not have the tool that would let us check whether the island result holds in full generality, because we do not yet have the full theory. This is not a minor technical gap. It is the central gap in quantum gravity as a field. And the island result, for all its power and elegance, sits on one side of that gap. The question of whether it crosses to the other side, whether it describes what actually happens in our universe, is not yet answered. The de Sitter problem, and why it's the big one. Then there is the deeper disagreement. The one that, if I'm being candid, I think is the most important open problem in theoretical physics right now, and the one that gets the least attention in popular discussions of the information paradox. Our universe has a positive cosmological constant. It is expanding, it is accelerating, and it is, geometrically speaking, a de Sitter spacetime, or asymptotically approaching one. This matters enormously for the information paradox, and here is why. The entire island calculation, the entire toolkit of ADS/CFT, the Ryuta-Kayanagi formula, the replica wormhole technique, was developed in anti-de Sitter space, a DS space, a space-time with a negative cosmological constant that curves inward, like the inside of a bowl, and has an asymptotic boundary at infinity. The boundary is where the holographic dual theory lives. It is where the lower dimensional description resides. The whole framework depends on having that boundary. It is not a technical convenience, it is structural. The duality between the bulk gravity theory and the boundary field theory requires the boundary to exist. De Sitter space, our space-time, has no such boundary. It curves outward, like the surface of an expanding sphere. Every observer in de Sitter space has a horizon, a cosmic event horizon, currently about 46 billion light-years away, beyond which the expansion of space is carrying things away from us faster than light can bring information back. Things cross that horizon and are, from our perspective, gone. And the question of whether the information that crosses our cosmic event horizon is preserved or lost is the cosmological version of the information paradox. It is the same question, applied to the universe itself instead of a black hole, and it has no established answer. Susskind published a paper in 2023 attempting to formulate a version of holography for de Sitter space. His approach is observer-dependent. Each observer in de Sitter space has access only to their own causal patch, bounded by their cosmic horizon, and the framework assigns each observer a finite-dimensional Hilbert space describing their accessible region. Time reversal becomes a gauge symmetry in this picture. It is a bold and creative attempt to find the de Sitter analogue of ADS/CFT. It is also, as of 2026, highly controversial and far from established. The community has not converged on it. The mathematical structure is not as clean as ADS/CFT. And it is not clear that the tools that made the island calculation work in anti-de Sitter space have any direct analogue in this framework. Let me be precise about why this gap is so significant, because it is easy to hear the calculation was done in the wrong space-time and think it is a technical footnote. It is not a footnote. Anti-de Sitter space has a boundary. The holographic dual lives there. De Sitter space has no boundary. The holographic dual, if it exists, has a completely different structure, and nobody has found it. Ed Witten wrote about this problem in 2001. More than 2 decades later, it remains open. The greatest living theoretical physicist in the world identified this as a fundamental problem in the year that most of the students at the Stony Brook workshop were in elementary school, and the field has not solved it. That is a measure of how hard it is. The wire. We can't see. There is another gap that bothers me more personally, and I think it should bother you too, because it is the gap between having an answer and actually understanding what the answer means. The page curve falls out of the Island calculation. The information is preserved. We know the shape of the entropy curve. We know that information escapes. What we do not know is the channel, the physical mechanism, the wire. Here is a concrete way to think about it. Suppose you drop a single specific word, say, the word encyclopedia, into a black hole. The Island picture tells you that word's information is preserved in the Hawking radiation outside. It tells you the entropy of the radiation follows the page curve. It tells you the total information budget balances at the end. What it does not tell you is which specific Hawking photons carry the information that the word was encyclopedia, and not biography. What quantum event, at what moment, encodes that specific bit of distinction into the radiation field outside the horizon? What is the physical process, at the level of individual quantum transitions, that takes a specific interior configuration and imprints it, scrambled but present, onto a specific pattern of exterior photons? The calculation says the encoding happens. The calculation does not say how. It is like being told with complete certainty that a message was transmitted and received, and knowing with precision what the message said, without having any idea what the wire looks like or how the signal travelled through it. The endpoint is specified. The mechanism is dark. This is not a criticism of the Island picture, it is a description of where it leaves us. And where it leaves us is with a result that is mathematically rigorous and physically incomplete at the same time. The shape of the answer is known. The physical story of how information moves bit by bit, photon by photon, from the interior of a black hole to the radiation outside it, that story has not been told yet. And telling it would require a degree of microscopic control over the quantum gravity calculation that no current theory provides. ER equals EPR, conjecture, not theorem, and then there is ER equals EPR. The proposal that wormholes and entanglement are the same thing, viewed from different angles. The idea that the space between any two entangled particles is threaded by a Planck-scale Einstein-Rosen bridge, and that what we experience as spatial distance is the collective geometry of an incomprehensibly vast network of such connections. It is, I think, the most beautiful idea in contemporary theoretical physics. The evidence for it is indirect but accumulating. The Gauss-Jafferis wall traversable wormhole protocol, the SYK model results, the Caltech quantum processor experiment in 2022. But it remains a conjecture. Maldacena and Susskind were careful about this when they wrote the original paper. They called it ER equals EPR, not ER equals EPR theorem. The mathematical identity between wormholes and entanglement has been demonstrated in specific models, in specific contexts, where the holographic dual is known and the calculation is tractable. Whether it is literally true in complete generality, whether every entangled pair of particles anywhere in the universe, including the entangled photons in a laboratory optics experiment on Earth, is connected by a microscopic wormhole, has not been proven. And this matters enormously, because if ER equals EPR is literally and universally true, then the entanglement structure of the quantum vacuum, the vast network of quantum correlations between fields at every point in space, is the geometric fabric of spacetime. Every distance is an entanglement count. Every dimension is an emergent property of correlation patterns. The universe, at its deepest level, is an information structure, and geometry is what that structure looks like from the outside. If ER equals EPR is a powerful analogy that captures something important but is not the full story, if it holds in some regimes and fails in others, then we have a useful tool but not a fundamental principle, and the deeper story is still missing. The distinction between those two possibilities is not resolvable with current mathematics. It is one of the places where the field is genuinely in the dark, not just filling in details. The observational frontier is closer than you think. Here is the thing about all of these open questions that I find genuinely exciting rather than discouraging. They are not going to stay theoretical forever. The next generation of observational tools is going to start putting real constraints on these ideas, not in decades, in years. LISA, the Laser Interferometer Space Antenna, was formally adopted by the European Space Agency in January 2024. Construction began in 2025 after a prime contractor was selected. LISA will be the first space-based gravitational wave detector, and it will operate in a frequency range completely inaccessible to ground-based instruments like LIGO, the millihertz band, where the gravitational waves from supermassive black hole mergers live. We are talking about black holes millions or billions of times the mass of the Sun, colliding and merging, producing gravitational wave signals so powerful that LISA will detect them from anywhere in the observable universe. But the observations most relevant to our story are called extreme mass ratio in spirals. These are events where a small compact object, a stellar mass black hole or neutron star, spirals slowly into a supermassive black hole over thousands of orbits. The slow in spiral means LISA will track the gravitational wave signal for months or years, accumulating extraordinary precision on the orbital dynamics. And a 2026 paper analysing LISA's capabilities found something remarkable. Given sufficient precision, LISA's measurements of these inspirals can distinguish between a true Kerr black hole with a smooth event horizon and a fuzzball, the string-theoretic alternative where the interior is replaced by a Planck-scale tangle of stringy excitations with no conventional horizon at all. Two competing resolutions of the information paradox. One observatory, observable difference in principle, that is not a distant aspiration. LISA is being built right now. And then there is the next generation Event Horizon Telescope. The NGEHT is targeting operations in the late 2020s and early 2030s. It will expand the catalogue of directly imaged supermassive black holes from 2, Sagittarius A star and M87 star, to something like a dozen. It will operate at 345 GHz, giving a 50% improvement in angular resolution over the current instrument. That improvement may be sufficient to image not just the black hole shadow, the dark region we saw in the famous 2019 image, but the photon ring. The photon ring is a series of higher-order lensed images of the surrounding matter, stacked concentrically just outside the shadow, each formed by light that has orbited the black hole one more time before escaping. The photon ring encodes information about the black hole's spin and geometry with extraordinary precision. It is, in a sense, the black hole's fingerprint. And there are proposals for space-based extensions of the EHT that would achieve angular resolutions fine enough to see structures in the ring-down of the photon orbit, features that theoretical models predict would carry observable signatures of quantum gravity corrections, features that would look different if the black hole has a conventional horizon versus a fuzzball surface versus a firewall. We are not waiting for the physics to become testable. The physics is actively becoming testable. The timeline is years to decades, not centuries. The questions that Hawking put on the table in 1974, questions that seemed permanently beyond the reach of any conceivable observation, are entering the era of empirical constraint. What a revolution looks like from the inside. I want to close this section with something that I think is important to say plainly. We are not in the position of people who have solved the problem and are filling in the remaining details. The popular science framing of the island results sometimes implies that the information paradox is closed, that the field moved on, that the answer is in. That framing is not accurate. It is not what the Stony Brook workshop reflected. It is not what the honest accounting of the open problem suggests. What we are in is the middle of a revolution, and revolutions from the inside do not feel triumphant. They feel vertiginous. You have a result that clearly points toward the answer. You have mathematical evidence that is compelling and accumulating. You have a consensus that is strengthening. And you also have a four-dimensional gap you cannot close, a space-time that your tools were not built for, a bit-level mechanism you cannot describe, and a conjecture about wormholes and entanglement that is beautiful and unproven. That combination, compelling partial answer, genuine remaining darkness, is exactly what the inside of a scientific revolution looks like. It is not a comfortable place to be, it is an honest one. And honestly, I think that's more interesting than a clean solution would have been, because the questions that remain open are not clean-up questions. They are questions about the structure of space-time, the nature of information, and the geometry of the universe we live in. The clean-up questions came and went decades ago. What's left is the real thing. Part 12. The universe has no private spaces. There is a shelf somewhere, probably in John Preskill's office at the California Institute of Technology, with a copy of Total Baseball, the ultimate baseball encyclopedia on it. It has been there since July 21st, 2004. It arrived as the payment for a bet that Hawking said was settled, and the room knew wasn't. It has been sitting on that shelf through 15 years of work that finally, in 2019, produced the derivation that nobody in Dublin had that day. And it is, in its way, a monument to the patience that real science requires. Let me tell you what that encyclopedia represents, now that we have come this far. Let me tell you what the entire 50-year history of the information paradox has produced, at the level of conclusions about reality that are supported by the mathematics. The information from everything that has ever fallen into a black hole, every star, every planet, every photon, every quantum state that ever crossed an event horizon, is not destroyed. It is preserved, encoded in the Hawking radiation that drifts through space around the black hole. After the page time, the interior of the black hole is encoded in that radiation. The inside and the outside are not two separate places. They are the same system, described from different angles, in the same way that a hologram on a flat film and the three-dimensional image it projects are two descriptions of the same information. The most hidden region in the universe, the thing defined by the impossibility of escape, has been broadcasting its contents into the radiation outside it, quietly, for the entire duration of its evaporation. The universe keeps its ledger, but the price for keeping the ledger is something we have to pay in our understanding of what space is. To make the ledger-keeping work, to make the information escape consistently, without cloning it, without violating the equivalence principle, without breaking quantum mechanics, we have to give up the simple picture of the inside and outside of a black hole as definite separate places. The interior, after the page time, is in two places in the only sense that matters in quantum mechanics. It is described by the same Hilbert space as the radiation. There is no single classical geometry that accommodates both descriptions simultaneously. The geometry has to reorganize, and the geometry reorganizes because geometry is not fundamental. Geometry is not fundamental. Space is not a background. The distances between things, the very concept of here as opposed to there, are properties of how the universe is entangled with itself. They are derived. They are what the entanglement structure looks like when you zoom out far enough to stop seeing individual qubits. Change the entanglement, and the distances change. Reduce the entanglement between two regions to zero, and the regions become causally disconnected in different universes infinitely far apart. Increase the entanglement, and the regions approach each other. At a critical density, they merge. Space is woven from entanglement. The fabric metaphor that everyone uses when talking about general relativity is literally correct, but the thread is not some mysterious continuous medium. The thread is quantum correlation. The fabric is correlations, all the way down, and the holographic principle says something about the weaving pattern that should stop you cold. The maximum information content of any region of space is proportional to the area of its boundary, not its volume. The three dimensions you experience as depth, the dimension that makes the room you are sitting in feel like a volume rather than a surface, may be, in some deep sense, a reading of a two-dimensional information structure, not a simulation, not a projection in the sci-fi sense, a derived property. The dimension count of the world is not a fundamental fact about reality. It is a feature of how you decode the underlying information. Think about what you're sitting inside right now. A room, presumably. Maybe a bed. The walls are at a certain distance. The ceiling is at a certain height. The objects around you are arranged in three-dimensional space at specific positions you could measure. According to the picture that the last 50 years of theoretical physics has been building, all of those distances and positions are not fundamental properties of a fixed space-time. They are outputs of an underlying quantum information structure. They are what the entanglement looks like. They are the hologram's projection. The geometry is real. It is measurably, concretely real. The same way the three-dimensional image from a hologram is real enough to cast a shadow, but it is not the most fundamental description of what is here. I want to put some numbers on the timescale of what I am about to describe, because the human imagination struggles with the relevant scales, and I think struggling with them is part of the point. The current age of the universe is about 13.8 billion years, or roughly 10 to the 10th years. A solar mass black hole takes about 2 times 10 to the 67 years to completely evaporate via Hawking radiation. That is 10 million trillion years. The ratio between the evaporation time and the current age of the universe is roughly the same as the ratio between the diameter of the observable universe and a single proton. The universe has been alive for a proton's width of the time it will take a stellar mass black hole to finish evaporating. Now imagine the deep future. The stars have been burning for 100 billion years, then 1 trillion years, then 10 trillion. Eventually the last star flickers out. The galaxies, without new star formation, gradually disperse their stars through gravitational interactions over 10 to the 14 years. After 10 to the 34 years or so, protons have decayed, and ordinary matter as we know it has ceased to exist. Only black holes remain, the supermassive ones at galactic centers, the stellar mass ones scattered through the darkness, and they are all slowly, patiently evaporating. And then, one by one, the stellar mass black holes reach their page times. The information from everything they swallowed begins, at last, to emerge in the radiation. The words of every star that ever fell in, scrambled beyond any practical decoding but present, mathematically, in the correlations between photons drifting through an almost empty universe. At 10 to the 67th years, roughly, a solar mass black hole formed in the early universe is in its final moments. Its Hawking radiation has been carrying scrambled information for the last half of its life, a period so long it makes the current age of the universe unmeasurable. It emits its last photons, the information from a star that died 10 billion years ago, that fell into a black hole in the first epochs of cosmic history, finally completes its journey. It is not readable. No technology could reconstruct the star from those photons, but it is there. The ledger entry is present in the radiation. The universe kept its word. This is not poetry. This is the implication of the mathematics, followed to its conclusion. The universe does not destroy information. It scrambles information. It holds information for timescales that make cosmic history look like a rounding error. But it holds it. The ledger is perfect and total. Now let me ask you something, and I want you to take it seriously as a question rather than as a rhetorical gesture. If the geometry of space emerges from entanglement, if distance is a property of correlation, if the dimensions you experience are derived from an underlying quantum information structure, then what is the quantum information structure that the universe itself is running on? What is the fundamental layer? What is entangling with what? The island picture says the interior of a black hole is encoded in the radiation. The holographic principle says the interior of any region is encoded on its boundary. ER equals EPR says the space between things is made of the correlations between things. All three of these results point toward a picture of the universe, in which the most fundamental description is not geometric, is not a space-time with things in it, but informational. The universe is, at bottom, an information structure. The geometry is what the information looks like when you read it in a certain way. The space you're sitting in is how the underlying correlations present themselves to an observer who is herself made of correlated quantum fields. This is not mysticism. It is the conclusion toward which 50 years of the hardest theoretical physics has been building. It is what you get when you take quantum mechanics seriously enough to ask what happens at a black hole, and then follow the answer wherever it leads. The question, what is a black hole, has turned into the question, what is space? And the question, what is space, is turning into the question, what is the universe, at the level beneath geometry? And that question does not have an answer yet. But we know more about what the answer looks like than we did when a wheelchair rolled to a podium in Dublin in 2004, and a room full of physicists watched a man hand over an encyclopedia and privately understood that the real question hadn't moved an inch. It has moved now. It has moved farther than Hawking or Thorne or Preskill imagined in 1997 when they put their names on a bet about an encyclopedia. It has moved from where does the information go to what is the space the information was in and why does it feel like space at all. The encyclopedia on Preskill's shelf contains the information about every baseball game ever played, every statistic, every season. In principle, in the quantum mechanical sense that the island picture demands, so does the Hawking radiation from every black hole that has ever formed. The universe is not a place where information falls through cracks. The universe is a ledger. The cracks were always our misreading of what the ledger is written in. We were not wrong about black holes. We were wrong about space. The black hole was the laboratory. The answer is about everything else. And the terrifying thing, the thing that should genuinely keep you thinking about this at 3 a.m, is not that the information is preserved. The terrifying thing is what we had to conclude about the nature of space in order to preserve it. The world you're sitting in right now, with its distances and its dimensions and its apparent solidity, all of it a reading of something simpler, something stranger, something that does not look like space until you stop looking carefully. The next time you look out a window and think about the distance between you and the horizon, between you and the sky, between you and whatever is out there beyond what you can see, remember that distance is not a fact about a fixed background. Distance is a property of how the universe is entangled with itself, and that entanglement is the ledger, and the ledger has no blank pages.